Hello. This is Nicholas. I'm really excited to make this video. I'm basically going to be telling you guys, giving some motivation to why the Laplace transform works, what it does, how it can be used to solve differential equations. So as an example, let's consider y prime plus y is 4e to the 3t. So y is a function of t. And there are a number of ways to solve this. For example, this is just a standard old linear differential equation. It's also a Bernoulli equation. But let's do it with Laplace transforms. So the idea is, really what it comes down to is, wouldn't it be nice? What makes this equation, or really differential equations in general, difficult is the fact that we have this y prime and we have this y. They don't go together with each other. If we were to somehow transform this y prime into a y while keeping this y the same, we would just have y plus y equals 4e to the 3t. And that would be very easy to deal with. You just divide by 2 and you get y. So we need to get rid of this y prime. That's our goal here. So if we were to get rid of this y prime, well, we could do one thing. We could integrate both sides. So we'd have to integrate, and these would all be with respect to t. But so this is good and all because now we have a y, but then we have the integral of y dt, and this can be easily integrated. I'm not going to worry about that. So the problem is I would like to write everything either in terms of just y, or in terms of just the integral of y dt. So the idea is that I need to integrate y prime more times than I need to integrate y, right? I could say integrate y prime twice and integrate y just once. If there's some formula for integration that lets me do that, then everything could be written in terms of the integral of y, and then it just becomes an algebra problem, and you differentiate at the end to get y. So is there really, what I'm asking is there a formula for integrals with an integral on the other side? So we integrate more than once, in other words. And there is. It's the integration by parts, right? The integral of u dv, u dv is uv minus the integral of v du. So the idea is that this is a, let me fix that. This is a v. So if we let dv be the derivative of y, then what we are having, see, we're integrating y prime twice essentially, and we're only integrating u, or whatever else whatever we're going to let u be. We're only going to integrate u once, because look at, so if u is, or if dv is y prime, I don't really care about what u is right now. I'm going to get to that later. So we have the integral of u y prime is let's see, that's uy minus the integral of y du, whatever du is. So we pick dv to be y prime, and so now when we integrate this, both sides of our differential equation, we will just have everything, we'll just have everything in terms of the integral of y, except for this y here, which I'm going to get to. So we can write everything in terms of the integral of y. But we also, we need to deal with this du here. We need to pick what that's going to be. And it needs to be something. See, the idea is we want to turn this differential equation into an algebra problem, basically. So if we can pick a du so that when we integrate it, it doesn't fundamentally change the form of the integral. In other words, we could still combine them together, and maybe we'd have a constant or something out front, but we would still be able to combine them together. So basically, we need to pick a u and a du so that when we differentiate and when we integrate, they are just scalar multiples of one another. So is there a function whose derivative is a scalar multiple of itself? Well, of course, that's all functions of the form e to the st. So if we take e to the st y prime, and I'm actually going to make it a negative st, because then when we take the derivative of e to the negative st, when we take it right here, then the negative will come out here and it'll make it a plus. And so plus is, we like plus signs. We don't like negative signs. They always mess us up. Maybe that's just me. So integral of e to the negative st y prime dt, when we do integration by parts on that, when we do integration by parts on that, oh my goodness, we get, what the heck? Y e to the negative st, yes, plus s times the integral of y e to the negative st dt. So, this is all well and good, but this y, let me get rid of this underline here. This y right here is still messing with us because we want to have everything in terms of the integral of y dt. So we could either write it in terms of the integral of y dt, or we could turn this function y with some mathematical operator into a number. And so how could we do that? Well, we could look at these integrals. Right now they're indefinite integrals. They don't have any bounds of integration. But if we were to make the integral definite, then all of this schmozkin right here would just be a number. Okay? Or it would be in terms of s. I mean, you could pick whatever s you'd like, but it would just be a number. So let's make the integral definite, right? So let's take the integral from a to b of y e to the negative st dt. That's going to be, by integration by parts, y e to the negative st, evaluated from a to b, plus s times the integral from a to b of y e to the negative st dt. So if we look at this, we really just want to choose convenient a and b's for ourselves. So, I mean, let's look at b first. If you notice here, so we don't know what y is, but we are saying to ourselves, well, let's look at this e to the negative st. I mean, what nice things could we plug in for t here? Well, I noticed that as t approaches infinity, then y, or the e to the negative st, that just goes to 0, right? Because you have 1 over e to the positive st. So it should make sense to let b be equal to infinity. That would be a nice number for us to pick. On the other hand, if we choose a being equal to 0, then e to the negative st evaluated at t equals 0 just gives a 1. So, I mean, 1's a pretty nice number. So let's pick a to be equal to 0 and b to be equal to infinity. Then we get the integral from 0 to infinity of y e to the negative st dt is y e to the negative st evaluated from 0 to infinity plus s times the integral from 0 to infinity of y e to the negative st dt. So if we evaluate this stuff, we plug in infinity here on this first bound here, and we're going to get 0. And then we put a negative because we're subtracting because it's the second bound. We just get negative, we'll just call it a y of 0. We don't know what y is, but whatever y is, plug in 0 into y and you're going to get a number. But it's important to know that this is just a number, whatever y happens to be defined as. So we have plus s times the integral from 0 to infinity of y e to the negative st. And this part right here, that part right there, not including the s, but this part right here, the actual integral, it's the Laplace transform. We write it as a big L like this. It's the Laplace transform of y. So this is convenient for us because now we can take the Laplace transform of both sides of this differential equation and then undo that, and we can get a solution because now we have everything in terms on the right side at least of the see, this whole part right here is the left side of the differential equation, and everything here is either a number or in terms of the integral of y. So it really becomes an algebra problem basically, and we can solve for the integral of y and then just differentiate, and we will get what y is the solution to the differential equation. So of course, I want to write it out just to emphasize its importance. The Laplace transform of y, typically, instead of y, they'll write it as f of t. So f is a function of t. Usually they interpret it as time. The Laplace transform of f of t is the integral from 0 to infinity of f of t times e to the negative st dt. And so I hope you can see that this isn't just some definition that I'm pulling out of thin air. This is where a lot of textbooks will start. They'll just start at this right here, and they won't give the background of what I've done here to get that. So I hope you can look at this and you could go, wow, that's a very natural definition. That really will help. And the idea, I just want to say it, is to turn it into an algebra problem. Or really, that's the idea with the Laplace transform. So now we need to pick. I'm going back to here now. So s is just some constant, right? The s was introduced when I said basically that I needed a function whose derivative is a scalar multiple of itself, and that was functions of the form e to the negative st. So s is just a constant, and so we need to let's pick a value for that constant, preferably a nice one. I mean, let's just say, let's say s be equal to 2. So then the actual Laplace transform part becomes the integral from 0 to infinity of y e to the negative 2t dt. So if we interpret this, I mean, this is really just some area under some curve. And let's say this area is 5. I mean, I'm just pulling a number out of thin air here. So what would that curve look like? Well, maybe it would start here and then go up and then down like this. Maybe it would go like that. Maybe it would go like that. So the point I'm trying to make here is if we just pick a value of s, there is an infinite family of curves that satisfies this condition here. So we need more than that. We would instead actually just leave s as a variable. And the reason why we don't pick a value for s and leave it as a variable is because then the fact here that I have written must be true for all values of s. And that tells us a lot more information than if we just say s equals 2. That restricts us infinitely much, actually. So if s is a variable, it turns out that there is only one function, y, whose okay, let me say it like this. What I'm saying is that the Laplace transform is unique. So there's only one function y whose Laplace transform of y is, say, some function in terms of t. Only, or it would be in terms of s when we go to evaluate it. So only one function y whose Laplace transform is f of s. So when we go to see, we've taken, we had this differential equation here. Y prime plus y is 4e to the 3t. So I go and I take the Laplace transform of both sides. And so I take the Laplace transform of both sides. Let me look at this one first. When I take the Laplace transform of 4e to the 3t, first of all, notice that the Laplace transform is an integral on itself. It's defined through an integral. So when we have 4 times, basically we're going to be getting that this is e to the negative st times 4e to the 3t dt. That's that integral evaluated from 0 to infinity. But with integrals that we can pull that constant out front and make it 4 times the integral from 0 to infinity of this will be e to the 3 minus st dt. So the point I'm making here is we could have just written it as 4 times the Laplace transform of e to the 3t. So basically, you can put a constant inside the Laplace transform, and since it's defined through an integral, just put it out front, just like how you do with integrals. So now this is going to give me 4 over 3 minus s. And now I'm going to plug in the bounds. So we have e to the 3 minus s t from t equals 0 to infinity. So when t equals infinity, the whole thing goes to 0. Let me instead, to show that, if I write it as a negative s minus 3. See, if I have that negative out front, then the negative t will become a negative infinity, and that's 1 over e to the infinity, so that thing goes to 0. So, and then for the 0 bound, I'm going to put the negative sign here. We plug in t equals 0, we just get e to the 0 or 1. So the Laplace transform just becomes 4 over 3 minus s. And that's pretty nice. I I flipped it here, my bad. It was 3 over s, and then I don't know why I wrote it. I was thinking ahead. So now we flip it, and now we get a s minus 3. So yeah, okay. Yeah, and that works. So the Laplace transform of 4e to the 3t is 4 over s minus 3. And that suggests that if I get rid of the 4's here, that the Laplace transform of e to the 3t is just 1 over s minus 3. Okay, so, and now I take the Laplace transform of y prime plus y. And another property I want to show is that since this is defined as an integral to begin with, and since the integral is a linear operator, in other words, integral of f sub 1, where f sub 1 is a function of x, plus f sub 2, also a function of x, dx, is the same thing as integral of f sub 1 dx plus integral of f sub 2 dx. That's what we mean when we say a linear operator. Then the Laplace transform has the same property since it's defined through an integral to begin with. So we can write this as the Laplace transform of y prime plus the Laplace transform of y. Oh, I wrote equals. My bad. Plus the Laplace transform of y. So the Laplace transform of y prime, is the integral from 0 to infinity of y prime e to the negative st dt plus the integral from 0 to infinity of y e to the negative st dt. And so I'm going to look at that one first, and I'm going to say integration by parts, right? And I think I did that up here, but I'll do it again here. So we have a differentiate and we integrate. I'm going to integrate y prime. I'm going to differentiate e to the negative st, and we have plus, minus. I integrate that, I get y. I differentiate this, I get negative s e to the negative st. And so that first integral becomes y e to the negative st. And then we have minus and minus, so that's plus. I can pull the s out front. That's s times the integral from 0 to infinity of... oh, and by the way, this is evaluated at 0 to infinity. Plus s times the integral of y e to the negative st dt. And then this is another integral from 0 to infinity of y e to the negative st. And this is going to be equal to the Laplace transform of the right side, which is 4 over s minus 3. And I know I did it up here. This whole thing just evaluates to negative y of 0. And then I can make this plus s plus 1. That's what's so great about the Laplace transform, is that I can combine these two integrals. That was the whole point of defining it the way I did. So s plus 1 times the integral from 0 to infinity of y e to the negative st dt is 4 over s minus 3. So I can solve now for the integral of y e to the negative st, or in other words, the Laplace transform of y. And so after some algebra, it turns out that I get that the Laplace transform of y, in other words, this integral here, is y of 0 minus 1 over s plus 1 plus 1 over s minus 3. And so now we have this relation, and what we can do is if we we want to seek an inverse mapping now. In other words, we want to undo the Laplace transform, and then we can just get our y, which is the whole point. We want to solve the differential equation. So we basically ask ourselves, we would say, well, we would take technically, we write it as we take the Laplace inverse of all of this schmozkin. So we take the Laplace inverse of all this. And so on the right side, we just get y. And then now we say to ourselves, what when we take the Laplace transform, what function when we take the Laplace transform of it gives us y of 0 minus 1 over s plus 1. And then likewise, we say the same thing here. What function when I take the Laplace transform of it, I get 1 over s minus 3. And if you remember, up here, I said 4 times the Laplace transform of e to the 3t was 4 over s minus 3. And so therefore, the Laplace transform of e to the 3t is 1 over s minus 3. So we have a e to the 3t for this part here. That's e to the 3t. So the Laplace inverse of 1 over s minus 3 is e to the 3t. And you might write it like this. You might think to do this. I haven't gotten formally into Laplace inverses yet, but if I take the Laplace inverse of this part here, let me write it like this. I have y of 0 minus 1 times 1 over s minus negative 1. So y is e to the 3t plus, and this is a number so I can pull it out front, y of 0 minus 1 times, now we just have to take the Laplace inverse of 1 over s minus negative 1. I'm not going to prove this in this video, but I mean, if you just do some intuition here, we said that the Laplace of e to the 3t was 1 over s minus 3. So it should stand to reason that the Laplace of e to the negative t is 1 over s minus a negative 1, which is exactly what I have circled here. So, and it is true that this turns out to be e to the negative t. And that right there is our solution to our differential equation. So summing it up briefly, we, to solve using Laplace transforms, take the Laplace transform of both sides of our differential equation. We solve for the Laplace transform of y, or in other words, this integral right here, and then we undo that Laplace transform and we will get our solution y. I hope that you have found this video helpful. Laplace transforms are really, really cool when you